So, looks like everybody's pretty much found their seat. So I'll get started because there's a lot of material I need to cover. So welcome to SPU-Based Deferred Shading for Battlefield 3 on the PS3. My name is Christina Coffin. I work at DICE in Stockholm. And for about the last year, I've been working with the Frostbite team, primarily with the rendering team. I work as a platform specialist, so that means that I deal with a lot of low-level programming, not just for the PS3, but also our PC SKU and our Xbox 360 SKU. So here's our agenda. A few reminders to be courteous to everybody is to please turn off your cell phones or put them on silent mode. And also at the end, please fill out your survey forms. It's appreciated. So with the agenda here, first I'm going to do sort of a high-level overview first, and then when I go back into the practicalities and the algorithms and stuff, then I'll start digging into more detail. And then for specific optimizations to make this technique usable on PS3 and also not use too much SPU time as well, I'll go into specific code optimizations as well, and then best practices to make this efficient also from a time developer standpoint as well. And QA will obviously be at the end. So the point of this technique that I'm going to outline today is to accentuate the fact that the current console generation is going on 5 years, especially PS3. This fall is going to be 5 years old in the retail space, and for developers, we've had that hardware obviously 1 to 2 years ahead of time for that. So a lot of the sort of easy wins for optimizing things like using halves in your GPU shaders and so on, everybody's sort of done that, but our art directors and game designers obviously keep coming to us and saying, well, we want to keep doing more. We want more characters, we want more shaders, we want prettier lighting, we want something. And so the whole point of this technique is to sort of squeeze a little bit more visual power out of things. So before I get into that technique, sort of where we came from with this is for the previous iteration of the Frostbite engine was forward rendered. Very, very limited light source. We're talking about 2 3-point light system. And so the lighting, we couldn't really do a whole lot with it, so nighttime maps were very few and far between. But we did have destruction, and we definitely needed to keep that for Battlefield 3. Now, on the flip side, another forward-rendered game from DICE that a lot of people love, including myself, is Mirror's Edge. And that has really amazing lighting, but it has the downside of that it's pre-computed. And there's obviously no destruction in that game. So we wanted something that was going to improve the visual quality of the lighting towards the spectrum of Mirror's Edge and also maintain the destructibility. And especially for the Battlefield franchise, we needed to support vast, large environments and destructibility. So the solution for this is that we needed to build an engine that was going to handle indoor, outdoor, and also sprawling and urban environments with full HDR lighting. And we just decided to go with deferred shading because based on the lighting requirements that we needed and to decouple the geometric complexity and draw batches with the lighting, it was just the obvious choice. So I'm not going to spend a whole lot of time on what is deferred shading and why it's awesome. We're just going to go straight into the how to actually do a lot of this work on the SPUs. So there's a scene right here. Let's see. Sorry. We had, first of all, our DX11 compute shader implementation handled a lot of lights, but we wanted to also map this onto PS3 and do tile-based deferred shading with a lot of lights to light up environments and put lights on muzzle flashes, explosions, And the only way that that was going to happen was we needed to get the SPUs involved and offload some of the GPU work. So the overview of this is the core components. We're using a physically based shading specular model. We perform everything at full float precision. We do full HDR lighting, so we're not doing something like RGBK compressed lighting where you're trying to pack HDR lighting into only 32 bits. And we have 6 SPUs we can do this on. So the number of materials that we need to support are rather diverse. This is just a sample of 4 different core materials that we're using a lot of. For a specular, we have a normal default sort of white specular, and then we have a metallic version where we just multiply against the diffuse albedo color to give us a nice sort of metallic look to it. So the rendering frame timeline, just in a real quick block diagram here, is first of all, we have our geometry paths, and we need to populate that, all the MRTs with all of that data. So we start with that, and then we have a step after that where we, since we rendered those MRTs into local memory, we actually transfer them back to cell memory. So the SPUs can fetch them and do their work on them. So the next part with that is that the SPUs need to know when they can start their work. So we actually have the GPU signal our SPUs on when they can start that work. So that's also in the command buffer. So once that happens, all the shading jobs begin and they start doing their shading work. While that's happening on the GPU, we obviously need to have something useful for the GPU to do. So here's a couple examples of things like cascade shadow maps, particles, and screen space ambient occlusion based on our opaque geometry can run in parallel. So in the case that the GPU is going to run ahead and finish all of its work before the SPUs, we need to stop it and make sure that it waits for the SPU shading work to finish. So the way we implement that is we use a thing called a jump to cell for JTS, which most low-level PS3 programmers should be familiar with. So that's basically just going to make it sort of spin in place and not go anywhere. And what happens is at the end of that, the SPU that manages to finish the last tile is going to ungate that and let the GPU finish the rest of the work for the frame. So we've made sure that we have a synchronization model there that lets us keep doing our work without any artifacts or race conditions. So what exactly goes into the G-buffer? So here's an image of our layout. So a few key points to note is that our normals are in world space, but we do use Crytek's best fit normals technique. So we renormalize those, and then this also renders into tiled memory for maximum speed. Now, the last G-buffer is beyond the scope of this talk. I have a link to that, and that's related to our radiosity solution. Another thing is the material ID as well as the material ID parameter and the third MRT there means something completely different to each material, and so the SPU shading will reinterpret that in a different way. So a block diagram of the rendering flow looks like this, where we filled our geometry paths, but we wrote it to local memory to populate our Z buffer and all of our MRTs. Now, I said that we do a copy back to cell memory to get that accessible by the SPU, and that seems sort of silly because, well, why didn't you just render it to cell memory in the first place? And what we found is when you're trying to fill out 4 MRTs, that there's sort of a performance cliff that you kind of fall off, and we still come out ahead, sort of taking the long way around doing this roundabout process, and still come out ahead 2 to 3 milliseconds in terms of GPU savings. And then once that copy is done, then we do that inline D-word transfer, and that's where our SPU kernel knows that it knows to look for that address and say, oh, okay, well, the data has been copied, so now we can start our shading work. So now that we have all the data in cell memory, and then we have a ton of lights in the scene that we need to apply to all of that data, we need to figure out how to get all of that done on all of the SPUs efficiently and in a nicely distributed manner. So based on the local storage limitations that we have of 256K per SPU, we can only move a subset of that data into local store. So we settled on a 64 by 64 pixel size that I'll refer to as a frame buffer tile or FB tile. So this is a singular work unit that the SPUs are going to work on. And so it comes out to there's about 225 of these. So for each region, they first of all need to reserve a tile. They're going to transfer the tile, and since we rendered this in a tiled format, they need to detile it internally so we can work on it. So after that, we have this huge number of lights in memory that we need to determine whether they intersect these tiles or not, and then apply those lights to those tiles appropriately. We need to unpack that data because it's not in a format that the SPU ISA can operate on. So that's another step that we need to do. And then we need to transfer that out to somewhere so the GPU can take the final lit shade pixels and continue the rest of the frame. So for the work allocation, this is basically done by an atomic tile increment where we write to cell memory value. And it's sort of like a ticket machine where you take a number and you look at it, and that tells you what appropriate offset in the MRT data that we need to fetch for that 64 by 64 tiled pixel region. And this method is better than doing a static split because we'd have no idea what our scene composition is. We might be looking mostly up in the sky, and then all the expensive shading is on the bottom. So any sort of static split is not really going to work ideally because you would then have some SPUs that are idle and they've already finished their workload, and the other one is backed up doing all the hard work. So data transfer and detiling. This part here, this is a basic code execution timeline going from left to right. So first of all, we need to get our Z buffer in, and then we're going to wait on that, and then the SPU code's going to detile that into a linear format so we can have something that's spatially coherent and also in a nice linear format for efficiency of doing several of our shading algorithms. And so here we want to do a DMA for the MRT, have code executing at the same time. This is a pretty basic concept for people that have done SPU work, is that if you have a DMA in flight, you want to execute code and do useful stuff at the same time. So for the light culling, we need to determine the number of visible lights that intersect the volume and world space. Now, since we have access to the Z buffer, what this means is that we know that the near and the far clip plane of each tile is going to be a smaller subset of the near and far clipping plane of the camera for the entire screen. So what we end up with is a smaller frusta that we can then do an intersection test against each of the lights analytically and determine which lights intersect a tile and which don't, because there's no point in obviously calculating shading for lights if it's going to fall out of the influence range of the pixels within the tile. So for the actual shading work, we're doing the same exact stuff here that we're doing on the GPU, but we need to reformulate it in a fashion that the SPU instruction set can do it, and it also can do it efficiently. So we're not thinking of things in single pixels anymore. We're thinking of things in quad words and subsequently at least 4 pixels at a time. Now, there are some minor differences in float accuracy and rounding, but they're so insignificant that from a qualitative point of view and staring at many close-up screenshots of widely varying light intensities and so on, that it wasn't really an issue. So our core shading components, these are sort of a really high-level sort of view of the different types of things that we're doing in our shading work on the SPUs. And we can do texture sampling, but it has the problem of you're being local store limited on the SPU, so you could only sample so much texture. So ideally and in practice, we don't do this. But it's not really something that we do on SPUs. So for lights that sample from textures very heavily, we still do those on the RSECs. So the core shading that we've settled on is a 4x4 pixel quad. So we're doing 16 pixels at a time per loop iteration when we're applying all of these lights and shading. And again, as I said before, with people optimizing GPU shaders these days, especially for PS3, people do some things in half floats. And since the SPU ISA doesn't know how to work with floats, it only cares about integers, floats, and doubles, we do everything at float precision. So the other bonus of shading in this format here is that it's spatially coherent. So when we start doing lower level tests and branches, we're going to get as much coherency as possible when we decide to branch on material or other things. So here's the visualization of several things in our G buffers. And when I talk about the expansion process, a lot of this stuff in its native MRT format, when it gets to the SPU, is not in the proper format. Like I said, we do everything in float. What that means is you also need to shuffle it around into structure of arrays format, and we also need to convert it to float. So there's a lot of work with the shuffle bytes instruction and convert signed to float instructions happening. And so this is the two instructions that do a lot of work in terms of shuffling things around and getting into the right format so we can actually start doing the shading work. So the inside of the loop for the shading is once we've unpacked all that, we have a few different arrays of lights. And we're going to take those MRT encoded pixels that have now been converted to float, and we're going to apply all these lights to them, and then we're going to actually convert it to half float into a format that the RSECs can interpret once we're finished with this, so we can finish the rest of the frame. Now, a few notes on DMAing out the pixels is that we currently do this out to a linear format. So what that means is that we could do individual DMAs of 32 by 1 pixels, but we instead do a small DMA list to output all of these. And that saves about a millisecond of SPU time just using a DMA list versus just doing a bunch of single DMAs back to back. And once all of this is done, when we can finish the rest of the RSX-based rendering for our frame. So to elaborate more on all of the stuff that we could possibly be doing on the RSX while we're doing all of this SPU-based shading, there's a list right here, and our current budget is to spend about 8 milliseconds doing all of these other things you see right here. So we're never sort of running out of work to do on the GPU while we're shading on SPUs. And what this translates to for our SPU shading budget is that we have about 40 milliseconds of time that we can spend on the SPUs to do all this lighting and shading work. And just a quick note on the fixed overhead here of just the transaction of DMAing in the data, detiling it, unpacking it for shading, shading it with at least one light, packing it back into half floats, and finishing all that for a 720p buffer is going to take about 8 to 9 milliseconds. And then after that, when you add additional lights, it increments much slower. And our current budget, as I said, is 40 milliseconds. And based on the scene composition and the number of lights, this is a highly variable and subjective value that's really hard to quantify. I mean, I have scenes where I can have 700-800 lights visible on the screen, and a lot of them are distant, and it will only take 15 milliseconds. So it's a lot about how many lights you actually have, but actually how many lights are actually touching pixels, and how many of those are touching the same pixels within a tile. So for algorithmic optimizations, these are things that we had to do in terms of our data format and data traversal to make this more performant. So for tile light calling, originally this started as a single process where we just fit as many lights as we could into local store and then only did a single pass at the lowest tile level you see here on the far right, which is a 32 by 16 tile, which comes out to there's 1,920 of these. That proved to be a little too fine-grained, especially for a single pass when we started adding more and more lights and we started stress testing it and throwing like 1,000 lights at it. So we added another higher level calling test above that, which is at the 64 by 64 pixel tile level, because that's our singular work unit per SPU. So between these two, we can further refine the number of lights that are intersecting these tiles, because at the smallest level on the far right, those depth extents are much smaller than their parent tile 99.9% of the time. So we end up getting 8 smaller frusta to test against the lights compared to the larger single one for the 64 by 64 tile. So this is the basic flow again of what's happening with the DMA traffic on an SPU that's working on a tile, as well as the code execution, is that we're always going to have one batch that we're going to need to wait on. But we do 16 lights at a time because we pack these into a long linear array. So they're already been primed for easy DMA and also easy culling. So once we have that, we're going to take the up to 128 of those for that region, and we're going to set them aside in local store. So when we go down to the next refinement here, we've subdivided it into the 32 by 16 subtiles. So we have 8 of those, and what we do is we just create a light index list at this point of which lights are intersecting each individual subtile. So this is a simple test scene. Unfortunately, I wanted to show a really cool, awesome level like the screenshot at the beginning with the nighttime and the rockets and everything, but PR people wouldn't let me. So this is a debug visualization of how many lights are intersecting all of these tiles. Now, as you can see in the middle of the screen, especially at the vanishing point, we get a red debug value. It says there's 29 lights intersecting this tile. This is a pretty common thing, especially with high depth extents within a tile, because we're creating a frusta that's based on the near depth and then the far depth. And so that long frusta volume is going to intersect a lot of lights across a very, very long, expansive environment. So when we do our sub-refinement of that, and we call it the subtile level, we see that we've eliminated a lot of the lights because the depth extents, again, are much smaller for those tiles. And an interesting point here is that if you have one light that intersects a tile, and you eliminate that single light from a tile, that's a larger win than eliminating one light from a tile that has, say, 2 or more, because we can basically skip all of the work for the unpacking and the shading and packing the lighting work to FP16 and DMAing that out for the tile, because there's no point. There's no meaningful output for that tile. So when we go and sort of pull back here and look at the culling hierarchy that we have here, we first of all started at the camera frustum level and figured out what lights are intersecting that. And then after that, we have a coarse Z raster that we do on SPUs, which uses occlusion imposters that render to a 256 by 114 float buffer. And so what we can do is we can also take those light sources and those light source bounds and test them against there and eliminate those lights before they even get to the SPUs for the final two steps here that I have outlined. So the takeaway from all this is that one of the reasons that we're going aggressive with all of this is that we need to handle a large variety of very arbitrary environments, both indoor and outdoor. And this is something that I spent a lot of time on refining to eliminate all the edge cases. And it's a mix of brute forcing things to some extent, but also adding a very simple hierarchy on top of it. And for the debug visualizations, these are really key because we need something that, like a technical artist or a lighter or somebody else that's doing level design or performance that's not a programmer, that they can understand those metrics and then decide, to change the layout of the level, or decide that, well, if we're going to destroy a building, then maybe we want to take some of those light sources out along with that destruction. So algorithmic optimization, first one. It's number 0 since we're all programmers here, right? So when we talk about analyzing these tiles and figuring out what's in them, as I mentioned before with the Z extents, we also analyze what material IDs are resident within these tiles. And the reason we do that is that there's some materials that we do work on that is more expensive, like skin shading, for example, which implements a smooth step function. And in general, if you find out that there's only one material that's within a tile, then you're going to have a vastly simplified permutation of that. And the one thing that I really like about this is that we're sort of in a position here to change the permutations on the fly based on what is actually in the buffer. We're not back on the CPU trying to be speculative or just using an Uber shader and saying, well, we have to handle every case, and we just take the performance hit. So normal cone culling, what that is that we build a conservative normal bounding cone of all of the pixels in a tile, and we can use that to cull or remove lights that may influence that tile based on taking the light direction and comparing it against that bound. Now, that works really good, especially for things like sunlight, which is obviously a strong single directional light. And we can actually create some hint data that will drive our outdoor light shading to skip things like cascade shadow map fetches and so on a per tile basis, because we can find out if all those pixels are pointing away from the sun. There's no point in fetching a cascade shadow map in that case. So to illustrate this, simple shipping container, there's a directional spotlight on one side. And when we visualize the light intersections with that, we get something like this. And with the normal cone culling, what that's going to do is just basically remove all of the lighting influence from those tiles on the back side of that surface. And this is still a heavily normal map surface, and we still can get a lot of wins with this. But it's just sort of another layer of optimization that we're using here to further reduce the number of lights and shading work that we need to do for a tile. Another thing that's pretty common in a lot of games, even deferred shading games or forward rendered games that are only using a GPU, of course, is to only do diffuse lighting. Like if you have a big, huge explosion or lots and lots of deferred lights, you might want, in some cases, to lean on just only computing the diffuse lighting model for that to save cycles. And that is something that we can do. And we also have an optimization where we can take lights and smoothly interpolate out the specular contribution term for those. And then once we've done that, that light can then be binned into the non-specular lighting list, which will further increase the shading speed. So this one is specular albedo. It's basically an optimization to find if you have a case where you have matte material that doesn't matter how many lights you shine on it, you're not going to see any specular. We can then cast that light to be a diffuse one. But in my experience, a lot of artists like to make everything just a little bit shiny, so it may not be a win depending on your game or your environment, but we do see use for it in some cases. Now, this is a very low-level optimization that I was quite surprised by how useful it was. And what this basically is that we, at the very beginning, we calculate the attenuation term for those 16 pixels that we're doing. And if that value is less than 0, that means that all 16 of those pixels are outside the lighting influence of a light, so we can actually do a branch. Now, a lot of people say that, well, branches are kind of bad, but when you're working on 16 pixels at a time and you're trying to do all the shading work, it's quite a win. And so we got about 20 to 30% improvement on this. So a little code snippet here to sort of visualize this is that we have here in 4 quadwords the calculated attenuation value, and we're going to compare that against 0 to get a bunch of masks. So for each word here, we're going to get in either a 0 or all Fs. And so when we horizontally merge those across, and then we merge them vertically into a single quad word, we're either going to get a value that's either 0 or all Fs. And if it's 0, that means that all those pixels fell outside of that range. And so we can skip all of the shading work. So this is something we do very early at the beginning of right after we've unpacked the pixels before we descend into the lighting for the rest of the shading for each light to jump around as much of the shading work as possible. Another thing is with optimizing and lighting the clipping space is that there's light bleeding is a fair criticism of deferred shading, but there are ways to combat that, especially with using clipping planes or other people mark things in stencil. But that's on the GPU, it's not really ideal, and we wanted something that was going to be implementable and not be too performance heavy on the SPUs. So this case right here, we actually have a clipping plane into the wall, so we've calculated the clipping silhouette from a quad in the wall to the side and then extruded the clipping planes. So what that does is when we take the tile depth extents and we figure out if those tile depth extents are inside or outside of that shadowed region, we can, at a high level, remove that light from that tile because we know it's completely in shadow. And if we know it's outside of that or not in the boundary case, we can generalize the lighting for that light to not do the clipping plane tests. And so only the tiles that straddle the clipping volume area are the ones that we then need to do a clipping at a per pixel level. So this is really nice in terms of doing many of these is because we're not working in a sort of per pixel level. We're doing things, again, at an analytical, higher-level, tile-based approach. So there's a lot of culling, and so it's a fair question. Why so much calling? We have destructible environments. We blow a lot of stuff up. We're adding lights onto everything, flares, muzzle flashes, explosions. The sort of landscape and depth complexity in our environments is highly variable. So a lot of these culling and occlusion techniques are required for us to get, again, really stable performance. And we also need to be considerate of people that love to play snipers and will zoom in and look constantly across a very varied and very complex landscape. So this last optimization comes from the help of our friends at Criterion when I was sort of lamenting about the general sort of cost of implementing a proper POW that handles a lot of high-intensity values, and we need a lot of fidelity in our shading model. So what this really entails is that instead of doing our shading model and using POW, we've reformulated it to only use to replace that POW with an exponent, because a POW internally is an exponent and a log. So what this translates to when you're doing this on the SPU is that you're going to save quite a lot of instructions. So we saw an additional 20% boost of switching to this model. And in terms of the divergence, it's something that only at very low specular powers has a divergence sort of in the middle. And by the time you get to a specular power of 10, you're not really seeing an issue with that anymore. So it basically converges. Code optimizations. Again, structure of arrays, data-oriented design. Really important to get this stuff to work at a really high speed. A lot of this, we do have to shuffle and transpose this data into the proper format. We shade it. Loop unrolling. As I said, we're not working in single pixels here when we're writing this shading work like we do in a GPU. So at the minimum implementation is when we go to structure of arrays is to do this in a 4x1 pixel format. Now, the issue with that is that we're still going to have latency with our instructions. So we unrolled again. That addresses a lot of it, but it's really not good enough. So we finally settled on unrolling things even further and doing 16 pixels at a time. And then since a 16 by 1 horizontal span isn't really the greatest thing for spatial coherency, in my opinion, when we were calling things, we switched it to a 4 by 4 pixel quad shape. So again, the branching is expensive, but it's a huge performance win, especially when you have more and more and more materials that you're supporting. Because right now, we're supporting 6 materials. And now some of these are very simple things that we can basically add in or remove via select, but there's other things that are worthwhile to branch around. So in general, with all of this shading work, one thing that's a minor source of frustration is that it's very heavy on one side of the pipe because we're obviously doing a lot of ALU work here. And so that's very heavy on the even instruction pipe. So we're doing float multiply add, convert integer to float, and so on. And so the other pipe goes pretty idle in general. The most of the time it's being used is just to load things in and then shuffle them around to the right format. Just a few notes on that there are ways to obviously implement shifts, ors, and ands with clever shuffling and rotating. So don't trust the compiler. Look at the assembly, especially when you're doing this stuff. Lookup tables for unpacking data. As I mentioned before, there's a lot of the MRT data that's in 8 bits. And so what that means is, well, we have to unpack it to float. And, well, 256 lookup table entries is all we really need to implement this. And there is a way to wrangle the instruction set to put this all in the odd pipe, because the even pipe is already overloaded, as I said, with all of the ALU work, multiplying, adding everything in float, and so on. So there is a threshold for this to be worthwhile, but it's pretty significant, especially when you consider that if you're trying to implement transcendental functions or something like that with the SPU instruction set in one of your conversion functions, that you might just want to move something to a lookup table instead. So here's one example to illustrate the point of when we derive our specular power, we're doing a POW, and then we're doing a normalize. So there's a divide, a log, and so on and so forth in this. And we're just taking that 1/8-bit value and converting it. So that's totally worth lookup tabling. And if we add more functions, such as converting a normal component from 8-bit, and we need to convert it to float, but then we need to make it signed, that's again something that we could fold into a lookup table and be clever with shuffling to put it into the right place and convert it and not add any more pressure to the even pipe. So this optimization is something that came in very late, and it was due to the fact that as we kept specializing more and more of the shading code, we were sort of running out of local store very quick. So we had to come up with an overlay system. We needed position-independent shading code, or just think of it as small shading kernels, and to highly specialize this processing and basically do it on demand. Like we're looking at a single tile here. We know what the material composition is. We know what types of lights are intersecting it. So this mechanism allows us to literally pull in the best permutation of code that can handle the material and data composition and the MRTs along with the lighting. And this is, again, a really, really important optimization. Now, for the worst case, little perf number thing here is that this is done at the 32 by 16 pixel level. So at the worst case, if we were completely local store bound and we could only hold one code permutation at a time, we were constantly swapping in and out, it would only take us 1 millisecond of SPU time to do that. But thankfully, we have enough cache room that we can hold a decent number of these permutations in local store. So the overhead of doing the DMA and the subsequent SPU time to bring those in is not an issue. So how do we build these things now? We have to still author this in a Uber shader style format where you're sort of turning on and turning off functionality with define. So we feed it a master source file, and then we run it through the compiler, and we compile it as position-independent code. And this is going to output our object file and our binary, and this is something that in our work environment we can reload on the fly. So I can literally make a change in the code, compile it, build the permutation, and then reload it live while I'm looking at whatever and actually see immediately the performance improvement. Now, for us to ship, we obviously need to embed it into the ELF, so I also generate an includable version that goes embedded into the ELF. So best practices, to reiterate on this, is that these are things I found I needed to be efficient. And so, first of all, when I talked about the part with the slight difference in floating rounding and so on, but also supporting a rich feature set of lighting and materials and so on, our reference target that we still need to compare against is the GPU version, because we still do some of those lights, like the ones with heavy texture sampling. Those still happen on the RSX, so we need some kind of parity there. So one of the things is that we do support a toggle back and forth of forcing all the lights through the GPU path, and then this also validates the superiority of the SPU version, where we can shade much faster on the SPU, but also do some of that shading work in parallel with the GPU doing other stuff. And then another thing for finding bugs is obviously, well, do you want to run it on 1 SPU, 2 SPU, 3 SPU, and so on. And we still, again, need to maintain a single Uber shader version. And some with the debug visualization stuff that I mentioned earlier, that stuff is stuff that's actually generated by each individual SPU. So it knows how to generate command buffer data for those visualizations as it goes, which also makes things very useful. So these are several different things that we can obviously permute on. Which ones we pick or which ones you may pick if you implemented this entirely depends on what your lighting model is and what your light complexity is. So this is something that was largely driven by what the performance characteristics were of these different materials, and whether we did things with the select or whether we did things with branching in the SPU shading code. So a few quick words on SPU assembler. It is awesome, but in general, this is something you don't want to jump in too early and do, especially when you're sort of figuring out your data flow and whether you want to store some input data, such as your light data, in structural arrays or array of structures and back and forth. You still want to write this in smart, just plain vanilla C code and go to SPA at the end to figure out how much you can actually improve things. But in general, with our stuff is even with hand unrolling things, adding load prologues before you dive into a loop and so on, you can still get 10-15% more improvement on this and improve, obviously, dual issue. But in general, the SPU shading code, as I said, is very even pipe heavy, so you're never going to see full dual issue utilization unless your lighting model is super, super simple. So the conclusions here are that the SPUs can do all of this work, and this is work that we can do in parallel with the GPU doing other useful things at the same time. And I like to think of all of the SPUs when they do this work as they're just little small ALU shading units. They're like little tiny GPUs. And if you sort of shift your thinking into that, I think that really helps you determine how you can pull more visual fidelity out of the SPUs and also improve the visuals significantly for your game. And so I'd like to thank all these people, Johan Andersen, first and foremost, for embracing this technique and having done the DX11 compute shader version and the initial SPU implementation, and then letting me run crazy with it and optimizing it further so we could use this technique in Battlefield 3 for PS3. So here's a list of, we have a few more talks related to Frostbite stuff here, and I'm open to questions. Yeah.
Hello, very interesting talk. I think it's amazing job with the lighting culling. And I think you mentioned something that you have an GPU implementation of the same thing, right? So
the what?
The GPU implementation of the lighting as well.
Yeah.
So
we still maintain a GPU implementation of all of this.
I was curious, like, how does it compare to the SPU version? I mean, in terms of time, GPU time.
Well, in terms of, okay, so you want to know the performance delta between the GPU version and the SPU version.
Yes.
The issue with that is that it's highly dependent on your scene complexity. Like, if you normally do deferred shading on a GPU, you're usually using like depth bounds calling and stencil wrangling and stuff like that. But what we found is with lights that are extremely close, that are sort of floating in air and actually not touching any pixels, the GPU version performs significantly worse. The SPUs can literally, if you spend 40 milliseconds of shading time for an extremely high number of lights and then give that work to the GPU, we found cases where the GPU takes 60, 70 milliseconds to do the exact same scene. And it's highly dependent, and there are some cases where we actually want to move some of the lights, extremely small ones, especially if they don't span larger than, say, 16 pixels wide or something. We can throw those back to the RSX and just have them do them, so they don't have to filter all the way down through this system and then only touch a few pixels.
Okay, so in general,
yes,
SPU implementation is faster. This is what you're saying.
It's faster. It's also much more stable.
Okay.
The really important thing here is that when we have destructible environments and we destroy, like we blow a hole in the wall, and then we have close depth, and then we have extreme far depth, and then we have tracer fire and explosions and so on, we get this huge amount of overdraw if you were to just sort of draw light volumes on the GPU. And do that work, even with depth balance calling, it breaks down really fast. And with the SPU version, we found that that lighting case performs much more stable and much better on the SPUs because we have all of these calling techniques that know that those lights aren't touching any pixels. They're floating in the middle of the air, and we're doing this analytically. So we're not having to just sort of think of this as a fill rate problem anymore.
Okay, thank you.
Sure.
With the SPU version running so fast, being able to do 1,000+ lights,
yes.
How is the same content rendered on the Xbox?
So I was waiting for that. So for the Xbox, it's a rather lengthy explanation, but the sort of quick and simple version of that is that, first of all, we still have to do our geometry pass on the GPU. But then what I do is I write some special shaders that then do a tile-based gather and sampling and calculate the min-max depth extents. And then I also do a material classify. And then we also use part of their API to do a GPU signal to launch some CPU jobs that then look at that data because we've resolved that sort of aggregated depth and material residency information to memory. So we can have those CPU jobs look at that and call a lot of lights and make the subsequent GPU shading work much more efficient. So if you take a quad and there's 8 lights that are intersecting that, well, then we end up picking a permutation that does an 8x unroll of the lighting and then injects some of the lighting parameters into a texture, and then we have a light index texture that encodes additional lighting information. Those CPU jobs finish and then join back into the rest of the command buffer for the rest of the frame. So it does do sort of the same path of taking some of the GPU work, crunching it down, giving it, in this case, to the CPU, and then giving it back to the GPU in time to do more intelligent shading work than it would normally do if we just sort of tried to brute force everything through the GPU.
Thank you.
Hi. If you have this implementation on Xbox 360, I also presume you have this implementation on the PlayStation 3. And if you would just do that simple CPU optimizations only on PlayStation, do you then gain enough speed, because I mean, like you said, it's better doing it on the SPU, but it's not like 10 times, 100 times better. It's more stable, but in the end, how do artists work with this? I mean, on the Xbox 360, it's not going to be stable anymore because you have like those small optimizations, but I mean, I think it's very hard for the artists to work in this way.
Well, in our experience, okay, so the question is, you want to know like how the artists appropriately adjust their content.
I mean, wouldn't it have been enough to do like the optimizations you do on Xbox, do the same thing on PlayStation, and kind of have like the same system going to make more stability for the artists?
Well, I think the reality is that, well, first of all, the PS3 in our case is our lead console.
Yeah.
And then for mature console development at this point, we're still putting in the extra effort to do the best optimized implementation per platform. We can't write something a single way and just expect it to be performant on each platform. So we do spend a lot of time optimizing the 360 version just as much as we do the PS3 version.
So there's still other stuff going on.
Yes, there's a lot more stuff. There's way more stuff than I could cram in this time limit. So, but one more thing on that side is that I am planning to present more details about the 360 implementation at a certain graphics conference in Vancouver later this year.
Hi. I was wondering if you considered prioritizing lights by how important they were visually on the scene.
So the question is, which SPU, which things do we put on SPU versus which things we put back on the RSX?
To some degree, but even just completely ignoring a light, say, for instance, because it just was too small or for some reason just wasn't as important as a more prominent light.
Well, the core concept of this is that we don't have to make trade-offs and say, oh, well, let's throw away this light or bound ourselves by sort of getting rid of certain lights and then replacing them with a billboard sprite that's emissive to approximate that light source. So we have lots of ways we can sort of do level of detail on this. As I mentioned earlier, with sort of fading in or out the specular, if we have a very specific performance case that puts a lot of importance on certain lights or certain scenarios.
Okay, I was just wondering, because obviously there is still an upper limit to how much you can
there
do,
is an upper bound to this, but that's what our content creators are responsible for. We say you can spend this much time. So when I said the figure of 40 milliseconds of SPU shading time, if that's a distant view, then you can do like 2,000 lights with that. If it's an indoor, highly constrained view, and you want every single spark or something to do light, then that can fit in that budget. It comes down to what the scene composition is.
Okay, so they could assign priority to them, but it just wasn't going to really help them in this case.
It doesn't really help in practice. Okay. But we have cases where we could fade them out in the distance or something if it ever became an issue. So there's a lot of granularity in terms of performance optimization that can happen at the visual level and also at the detail level. Because if we have a tile that's really far away, we can say, well, we don't need all these lighting models. They don't really matter because it's not visually significant at that distance. So there's a lot of options that we can do at that point.
Okay, thank you.
Sure.
Hi, do you perform any lighting on your translucent geometry, and do you have the compute budget for those?
So the question was lighting on translucent?
Yes.
Or transparent geometry?
Yes.
So for transparent geometry, that's something we still do in a forward lighting fashion. There's different ways that we implement that, like for particles, for instance. Those are soft vertex lit. Transparent geometry, we can do that at vertex lighting level. We have a lot of options there. It, again, depends on what the visual target is and what the use case is, whether we're doing like thousands of shards of glass or we need something that's much more high quality.
Right. So do you have a set compute budget for those from a art direction?
Well, again, it's part of the entire frame budget. So if they make a specific part and they say, well, I want to make a glass house or something, then they'll pull back on other things. So we give them numerical budgets, and then they sort of are allowed to sort of steal from one thing and sort of pad another budget out further.
Thanks.
Sure. Okay, so I think that's it for the questions. So I appreciate it. One more thing is please fill out your survey forms. Your feedback is invaluable, especially to me. Thank you.